Hi there, so this video is going to be on the first part of section 6.2, 6.3, which will focus on separation of variables, so solving differential equations by separating the variables. And until now, we have looked at solving differential equations that are in the form of like dy over dx equals to some rule in terms of x, or f prime of x equals to a rule in terms of x. And our way of solving has been by integrating to come up with the general solution to the differential equation, where we'd put the plus c, right? We'd add the constant of integration to represent the infinitely many functions whose derivative would be equal to the differential equation that you started with. And then if you wanted to find a particular solution, you would need to know a point that would lie on the graph of the particular function that you're trying to find, and you could plug that point in to solve for a particular c. What we have not yet looked at is solving differential equations where dy over dx is maybe in terms of x and y, like in terms of multiple variables, or dependent on multiple variables. So we're going to look at solving differential equations that can be written in this form. So not necessarily presented to you in this form, but like through some algebra, they can be written as m of x, which is just like a function that's in terms of x, plus n of y, which is a function that would be in terms of y, times dy over dx equals to 0. So again, not necessarily presented to you in this way, but could be written in this way. Kind of like with like how linear functions, like their equations can be written in the different forms of like standard form or slope-intercept form. Like you can rearrange the terms. So differential equations that we are going to use this next approach to solve can all be written in this form. Okay, and this new method for solving differential equations we call separation of variables. And exactly how it sounds, it's because you are thinking about separating like all your x variables and all your y variables, so that you can then integrate with respect to the variable that's on that side of the equation. So we'll start with something very simple. So if we have dy over dx equals to x over y. So previously we would not have known how to solve this differential equation because dy over dx is in terms of x and y. However, if we think about trying to get all the y's on one side of the equation, so let's say the left-hand side of the equation by multiplying by y on each side, and then the x terms on the other side of the equation, we would have y, let's try this again. So we would have y, sorry, my Apple Pencil wasn't working there for a sec. So we'd have y dy equals x dx, okay? And then from here, we can think about integrating each side of the equation. The left-hand side, we would have y squared using power rule for integration, y squared over 2. You technically can put plus c, but you don't have to. We can just put it on the right-hand side. So when we integrate, we'd get x squared over 2 plus, and I'm going to put plus c sub 1, okay? And you'll see why in a second here. Now, we often like to get our solution in a specific form that's maybe more recognizable to us. Like we could look at this and go, oh, well, if we were to multiply by 2 on each side, then we would get rid of the coefficient of 1/2 on the y squared and the x squared term. And we can do that. So like if we thought about multiplying by 2 on each side of the equation here, we would have y squared equals to x squared, and then you would want to put plus 2 times c sub 1, which actually is not necessary, because if we think about what c sub 1 represents, it's just the constant of integration, right? It represents any potential constant that we would end up having after integrating. So 2c sub 1, we can actually just think of as being c. I always think of it as like that constant of integration can absorb whatever other constants it comes in contact with. So really this can be written as, and if we wanted to get this in a more familiar form, like y squared minus x squared equals 2c is how the general solution can be written. And if you recognize that, this actually represents a hyperbola, and it would be a hyperbola that would open up and down. But this would represent the general solution to that differential equation. And we just solved by using separation of variables. Okay, so the next one, notice that in the equation we have y prime. And also notice that it's not in the form, well, neither was the first one, not in this form. So definitely not always presented to you in this form, but you look at it and you're like, okay, well, y prime is dy over dx. So I'm going to rewrite this as y times dy over dx equals sine of x. I'm like, okay, well, if I thought about multiplying by dx on each side of the equation here, I would have y dy, I don't need the, equals to sine of x dx, where then we're set up, now we can think about integrating. And left-hand side would be y squared over 2. And then thinking about integrating sine would be negative cosine of x plus c. And if we wanted to multiply by 2 on each side, we could either leave as is, or like, let's say that we were trying to match an answer for multiple choice. Like we could multiply by 2 on each side of the equation, and that would leave us with y squared equals to negative 2 cosine of x. And the c will absorb the 2, right? Because 2c is actually just c in this case. So just having the plus c to represent the constant of integration. For this one, if you want to pause the video and try it on your own, you can. And then I'm going to talk you through it. Okay, so again, we have the notation for the prime notation. I prefer to, when I'm using separation of variables, rewrite as dy over dx. And I know that I need to use separation of variables because dy over dx is in terms of x and y. So I'm like, how can I rewrite this so that I'm allowed to integrate with respect to y as well as integrate with respect to x? So in this case, if we were to multiply by 3y squared on both sides of the equation to get 3y squared dy on the left, and then multiply by dx on each side of the equation to have x squared plus 2 dx. Make sure you have your grouping symbols there around the integrand, so that then when we go to integrate, we would have y cubed, right? The 3's would cancel, equals x cubed over 3 plus 2x plus c. And we can just leave like that. Okay, same thing. If you want to pause and try this next one on your own, you can. And I'm going to also talk you through it. So first, rewriting y prime as dy over dx. Okay, and if I were to add e to the x over to the other side, because I'm trying to get the y dy by itself on the left-hand side, and then if I multiply by dx on each side of the equation, then I'm set to integrate. Okay, so that would be y squared over 2 equals e to the x plus c. And again, if we wanted to multiply by 2 on each side of the equation, just for the practice with that, that's still going to be like, I wouldn't write 2c, I would write just plus c. Sometimes you'll see where teachers will put, when they use separation of variables especially, will put like plus c sub 1, and then it's just after you've multiplied, then that just becomes the plus c, like what your final answer is for the general solution. Okay, a little bit different here. Again, if you want to try this on your own first, you can. But we're actually not finding just the general solution in this case, although we will do that first. We're going to find the particular solution. And the particular solution satisfies the initial condition, y of 1 equals to 4. This is just using function notation. So this is saying that on the graph of the particular solution, the graph is going to pass through the point 1 comma 4. Okay, so I'm going to rewrite using, instead of this radical notation, I'm going to use exponents. So x to the 1/2 plus y to the 1/2 dy over dx equals to 0. And then here's the step of separating. And you do not want to skip showing that you have separated the variables. That step does need to be shown. So here I would have y to the 1/2 dy over dx. You don't have to show every single algebra step, but you do need to show that you have separated the variables. So like from here, I can also think about multiplying by dx. Like you could go straight to this step here where you have the variables separated. And then we can think about integrating. And that'll be 2/3 y to the 3/2 equals negative 2/3 x to the 3/2 plus c. And from here, like if we wanted to add, especially if we recognize what we want to put the equation into a form that's more familiar to us, like with knowing what the graph would look like, or just to make it easier for finding the particular solution, like I might rewrite this as 2/3 y to the 3/2 plus 2/3 x to the 3/2 equals to c. Not necessary. We could have found the particular solution from here, but just you could. And then like if we thought about multiplying by 3/2 on each side of the equation, we would have y to the 3/2 plus x to the 3/2 equals to c, because 3/2 times c is just going to be c. Now here's the thing. So from this version of the general solution, I'm going to plug in the 4 and for y and the 1 for x. If I had solved for c back here with my first version of the general solution, that's fine. I just need to make sure that then I'm plugging that version of c back in there, right? Like I wouldn't have manipulated and then plugged that version of c back in here. That would be the incorrect c. So from here, if I'm plugging in 4 and 1, is that 2 cubed will be 8 plus 1, so c is equal to 9. And I just want to make sure that that goes back into this version of the solution. Okay, so this would be the particular solution that would pass to that differential equation that would pass through the point 1 comma 4. Okay, kind of similar. If you want to pause and try this one on your own, you can. So I'm going to separate the variables. So I'd have y squared dy equals x squared dx, and I'm set to integrate. So y cubed over 3 equals x cubed over 3 plus c. And from here, I can plug in the point, the initial condition, right, 0, 2. So we could do that. Or if I'm like, oh, I'm going to multiply by 3 on each side of the equation to turn this into y cubed equals x cubed plus c. We'll just make the algebra a little bit easier when we go to plug in 2 for y and 0 for x. Because then we see, okay, well, c is going to be equal to 8. Y cubed equals x cubed plus 8. Or you could have that written as like y cubed minus x cubed equals to 8. It's just whatever. If it's multiple choice, you want to get it to match. But otherwise, as long as you have the particular solution, you're fine. Okay, gets a little bit more complicated. Again, because just for solving a differential equation, like even if we had something, I know we've talked about this, but like if we had something like dy over dx equals to like x, you could think about separating the variables in order to find the general solution. Like we could rewrite this as dy equals x dx, and then think about integrating from there. And the left-hand side would become y, right? X squared over 2 plus c. So you can use like the separation of variables perspective with just solving a differential equation that's in the form of like dy over dx equal to a rule in terms of x. You just don't have to. Okay, so this one just asks us to come up with the general solution. So I'm going to first think about rewriting y prime. Okay, and then separating the variables, I would want to divide by the square root of 1 minus 4x squared and multiply by dx. So that everything in terms of x. So this is almost similar. It's more complicated looking, but similar to what we just looked at, right? Because we could isolate dy over dx and see that it's just, it's a rule in terms of x. But if we integrate from here, we'll have y equals, we need to do a little u sub. So if we let u equal 1 minus 4x squared, du over dx is negative 8x. We can say du over negative 8 will be equal to x dx. So rewriting this, that's going to be u to the negative 1/2 du. And then when we go to integrate, so negative 1/2 plus 1 would be 1/2. The reciprocal of that is 2. U to the positive 1/2 plus c. And then substituting what we had let u equal to back in. And there we go. Okay, and this is one you can, well, actually no, this one we should do, you should watch the video for this one. It's a little bit trickier. Or not getting to the general solution, but you'll see. Okay, so first off, rewrite y prime as dy over dx. Okay, and then separating the variables, I would have 1 over y dy equals root x dx. Or instead of writing that as root x, I'm going to write it as x to the 1/2. Okay, so we're ready to integrate. Oh no. So it'll be natural log of absolute value of y equals that'll be 2/3 x to the 3/2 plus c. Technically, this is the general solution, but we oftentimes like to have our functions in the y equals form, okay? Or this is a common one if it was multiple choice. This would not be an option for the general solution. Thinking back, so this is a log statement, right? We have natural log of y on the left-hand side here. We can rewrite in the equivalent exponential form using, right, the definition of a logarithm. So natural log, remember, is base e. So if we think this is e to this power would be equal to the absolute value of y. Let me relate this back. So like if we have log base b of x equals to y, remember, and this would be like the log form of this statement, the exponential form would be b to the y is equal to x, right? These say the same thing. So thinking that we would have absolute value of y is equal to e to the 2/3 x to the 3/2 plus c. And now this also technically still represents the general solution, but this is also probably not how you would see the general solution written. So thinking about exponent properties, we can rewrite the right-hand side here as e to the c times e to the 2/3 x to the 3/2. Now, because c is an arbitrary constant, e to the c represents an arbitrary positive number, okay? Right, because we have absolute value of y equals, so whatever the output is there is going to have to be positive. So we can actually think about replacing e to the c as just c. Like we could have had this labeled as c sub 1 and followed it through, and then we could replace that with like c sub 2 because we're going to go even a step further. But from here, if we wanted to drop the absolute value bars, we could have y equals plus or minus e to the c times e to the 2/3 x to the 3/2 power. So plus or minus e to the c power is also an arbitrary constant. Well, it's also it can't be 0. So we can actually just think about, like, I always think of it as e to the c is just c, but like that's c absorbing everything. So this is really can be written as y equals to c times e to the 2/3 x to the 3/2. And this is probably how you would see the general solution to that differential equation written. Okay, so we'll go through one. If you want to pause, try this on your own, you are welcome to. I'm going to also talk through this. It's a similar process. We want to get our general solution into the y equals form. So thinking about separating the variables, we would have 1 over y dy equals 4/9 dx, where then we can integrate. Left-hand side will be ln of absolute value of y equals 4/9 x plus c. This is technically the general solution, but again, rewriting in the exponential form, we would have absolute value of y equals e to the 4/9 x plus c power, which can be split by exponent properties as e to the c times e to the 4/9 x. Not all of these steps have to be shown, but I do suggest at least at first going through them so that you understand them. And if we drop the absolute value, right, that's plus or minus e to the c times e to the 4/9 x. This can just be thought of as our c. So our answer, or our general solution, would be y equals c times e to the 4/9 x. If you would like to use like the c sub 1, and like every time you replace, make it like c sub 2 and c sub 3, and then your finalized c, like that's fine. I don't need to see that, but you can if that helps you with understanding. So this would be our general solution to that one. Okay, next one's tricky. So looking at this, you're like, oh my goodness, x and y are both in the exponent position. What can we do here? Well, we do have exponent properties on our side, so we can rewrite the right-hand side as e to the x over e to the y, where now we can think about separating the variables so that we can integrate. Left-hand side will just be e to the y. Right-hand side would be e to the x plus c. And if we want to get into the y equals form, like it's going, we still back up here. Where'd I have it? Up here. But you can think about writing in the log form, right? We want y equals. And since the y is in the exponent here, we would have y equals the natural log of e to the x plus c. You could always check that going in the other direction, right? E to the y is equal to e to the x plus c. Okay, so from the 2006 exam, Form B, let's check this out. So we have all the tools to answer all these questions. Part A is from 6.1, slope fields. Right, so this is how it can appear on an actual exam. You'll notice they've only asked for 9 points in part A, where they say sketch the slope field for the given differential equation. Since it's really like not so many points, it's maybe worth it to just, instead of looking for trends, because you know how I said you could look for trends. I mean, actually, in this case, it wouldn't be so bad to think about, like, if dy over dx was equal to 0. Right? You can easily see that when y is equal to 1, dy over dx would be equal to 0. Meaning horizontal tick marks along y equals to 1. And then now we only have 6 points. So I would probably just make the table at this point. And plug each of those points in. So like -1, 0, 0, 0, 1, 0. I should have written smaller. Let's try this again. -1, 0, 0, 0, 1, 0, -1, -1, -1, 0, -1, 1. Okay. So plugging in, well, if I plug in 0 for y, it's always going to give me 1 for that factor in dy over dx. So I see think cosine of negative pi would be cosine of pi, which is -1. Okay. Why do I have... Oh, but if I plugged in 0. Oh, I see what I'm missing. Okay, so -1. So do my best to sketch slope -1. If we plug in 0, 0, okay. Cosine of 0 will be +1. Okay, and then 1, 0. Cosine of pi is -1. Okay, -1. Okay, so if we plug in -1 for y, it's going to be -2 squared would be 4 times cosine of negative pi, which will be -1. So -4. So I just need to make sure that that looks significantly steeper than -1. And then if we plug in -1, 0, okay, so that would be cosine of negative pi, which is cosine of pi, so -1. Did I mix that up? If I plug in 0, -1, 0. Oh, I already did that point. That was silly. I'm trying to do 0, -1. And then I'm trying to do 1, -1. I just mixed these up. Sorry. Okay, so that would end up being 4 times cosine of 0, which is 1, so 4. So that'll be steep. And then 1, -1 will be 4 times -1, so -4. Here we go. So that one needs to look pretty steep too. Okay, so you're just doing the best that you can with the tick marks and like just making sure your slopes of 4 and -4 look steeper than your slope of 1. Okay, so part B, there's a horizontal line with equation y equals to c that satisfies this differential equation. Find the value of c. There's a horizontal line with the equation y equals to c, so that we can read. So when y is equal to 1, yeah, then dy over dx would be equal to 0. So that means when c is equal to 1, I can say y equals to 1 satisfies the differential equation, so c equals to 1. Which it doesn't even ask for an explanation or justification, so you could just say c equals to 1. Okay, so for c, find the particular solution to the differential equation with the initial condition f of 1 equals to 0. So that means the curve that would pass through the point 1 comma 0. So this is a separation of variables. Sometimes they'll explicitly say like solve by separation of variables. This one did not, but looking at this, we have x and y, dy over dx in terms of x and y. So you should be thinking separation of variables. Okay, so we can rewrite this as 1 over y minus 1 squared dy equals cosine of pi x dx. And then we can integrate. If you want to pause here and try and integrate on your own, you can. I'm going to talk you through it. So both sides, we're going to need to do a u sub. So like if on the left-hand side, if I thought about doing let u equal to y minus 1, so du over dy would be 1, du equals dy. And then on the right-hand side, I'm going to say let z equal to pi times x, so dz over dx would be pi, where dz over pi is equal to dx. So I'll have the integral of 1 over u squared, or I'm going to actually write that as u to the negative second, du equals 1 over pi times the integral of cosine of z dz. So integrating negative u to the negative first equals 1 over pi sine of z plus c. And then substituting back in, we'll have negative 1 over y minus 1 equals 1 over pi times sine of pi x plus c. And then from here, we can plug in 1 for x and 0 for y. If we do that, the left-hand side becomes 1. If we plug in 0 for x for sine, then that becomes 0. So we'd get c equals to 1 when we plug that value in, which means the particular solution would be negative 1 over y minus 1 equals 1 over pi times sine of pi times x plus 1. Notice, and they will do this, they say find the particular solution y equals to f of x. So they want your particular solution to be in the form of y equals to a rule in terms of x. So you would not be done here. This is the particular solution, but we need in the form of y equals. So now this is an algebra problem. So like I could multiply by y minus 1 on each side of the equation. And then we could divide by the sine of x, pi times x over pi plus 1. So it would be negative 1 over sine of pi x over pi plus 1 equals y minus 1. And then to get rid of, you guys know how I feel about complex fractions, so we could just add 1 to each side, but we could also think about multiplying by pi over pi here to get rid of the complex fraction. So we would get y equals to negative pi over sine of pi times x plus pi plus 1. And that would be our particular solution in the form that they're asking, in the y equals form. Okay, so part 2 of this lesson I'm going to do in another video on the law of exponential change, and that'll be using our new approach for solving some differential equations, the separation of variables.